let's see here. So here, r equal 1, that means the modulus of z is equal to 1, right? This one means the modulus of z is equal to 2. So we got what? We got like, we want to have 20 equals to a times the natural log of 2 plus b, right? And we got 10 is a times the natural log of 1 plus b. Oh, well, that was nice. Log of 1 is 0, so therefore b is equal to 10, and 20 is equal to a log 2 plus 10, so math, a should be equal to 10 over log 2, right? So in short, we found that u of z equal to 10 over the natural log of 2 times the natural log, the absolute value of z, plus 10 is a solution to Laplace's equation on this annulus, which has 10 in the inside and 20 on the outside.
Can you explain why you use that equation again? Like, we know that part of the equation over there solves Laplace's equation.
Let me be a little more explicit here. This is actually 5 over the log of 2. I'll come back to your question in just a second. X squared plus y squared plus 10. Let me put it in more physical terms for you. If you had a conducting plate and you had an annular region of it and you fixed the inner voltage to be 10 volts and the outer voltage to be 20 volts, there's the voltage inside. Wait, is that the right thing to say? Voltage inside. Maybe that's the electric field inside. No, we don't know. No, it's the voltage inside. Why am I thinking the voltage has to be constant? What am I? Something I'm doing is wrong. Oh, something I'm doing is wrong. But anyway, I shut up about that. The math is good here. The physics might be wrong. I gotta do some soul searching about that. But
the electric field wouldn't be constant.
Well, I just said.
You're right. You said the voltage is constant. That wouldn't
Well,
make sense.
Maybe I shouldn't say conductor, but if I'm in a chargeless region, right? There's no charge in here, so that means Gauss's law, divergence of the electric field is rho over epsilon naught. So if that's 0 because there's no charge in here, then that's the divergence of the potential, the voltage function, right? So I mean, the Laplacian square root of the voltage is equal to 0. So I think this could be, this would be, for example, this could be the voltage function given 10 volts inside, 20 volts outside, if there's no charge in the middle.
Okay. Sort of like thinking like cross section of a tube, kind of. Oh, no, you said annular disk, never mind. Sorry, don't let me get bogged down in that.
It could be like, I suppose it could be like a coaxial.
Yeah.
Like a coaxial cable, like a cross section of coaxial cable where you had 10 volts on the inside and 20 volts on the outside. That would be the voltage between those.
Sorry, I don't mean to get you bogged down.
No, you're fine. And so to answer your question, again, we're solving a differential equation, right? So it's always a time-honored technique to just try to guess a solution. So my point is, this circular symmetry begs this kind of solution, but it's not a derivation, it's just an observation. Mm-hmm. But it's an observation which is born from a study of conformal mappings. Mm-hmm. But what this means, right, and the thing I haven't showed you guys yet, is that if, okay, so like, great, that's a solution on this annulus, right? What if you wanted to solve, instead of the annulus, what if you wanted to solve it on this strip? You know? Well, if you could find a mapping that took this annulus and tore it into this strip, I'm not sure you can, I'm just saying if you could. I'm not sure about that. I'm a little rusty. But the point is, if you can find a complex differential mapping from one shape to another, you can actually transport the solution of Laplace's equation on the initial shape to the second shape. And that's conformal mapping in a nutshell. It turns out there are like pretty standard boilerplate solutions. If you take the half plane, right, and you've got like little insulation points, and you got like voltage 1 here, voltage 2 here, voltage 3 here, voltage 4 here, and so forth, right? Like you can straight up write down a solution to Laplace's equation on like an upper half plane, where you're fixing different voltages on little subintervals. And then, because you know bilinear mappings, because you know fraction linear transformations, you can take that and you can solve a problem with a circle where you have differing voltages, like the same sort of things. By this technique of conformal mapping, you can map this solution to that solution. Now, solving this directly would be completely nuts, but there's like a standard kind of obvious thing you can do with arguments. For example, the argument. Argument is conformal. Argument is just, I'll leave it here with you guys. So like this one, right? Suppose you want pi volts here and you want minus pi volts over here. Arg of Z is your man. See, because I'm an idiot. 0 volts here. Pi volts here. They're better. I'm a little rusty with the complex. And you want to solve it up here. All right, so great. This guy gives you 0 on the positive real axis, and it gives you pi on the negative real axis, and it is the imaginary component of log z, which makes it a solution to Laplace's equation. So you want to solve Laplace's equation in the upper half plane with 0 volts over here and pi volts over here? That's your guy. Just like that. And I'm not sure what the straight up formula is for that right off the top of my head, but if you wanted to solve, I can tell you the formula for this one. If I wanted to solve, let's say pi over 2 volts here and minus pi over 2 volts there, right? Then I could just write down, I'll say V equal to inverse tangent of y over x. That will be a solution to Laplace's equation on this half plane, because it is the, this is the imaginary part of log z on that part of the plane. I should probably say little log z. Little log z doesn't commit to a choice of branch. So like, and this is the standard angle over here. And so, the imaginary part of the complex logarithm is the standard angle. So the standard angle function is consequently a solution to Laplace's equation. And there you go, it'll satisfy the boundary condition pi over 2 volts here, minus pi over 2 volts there, just like that. And if you wanted to, say, map to, if you want another problem, which was like this, you could just do like a rotation, and that would be a conformal transformation, and you could, I'll try to talk more systematically about how you actually get solutions from the z to the w or vice versa. This is the thing I forget, is like which one we start with and which one we end with, chicken and egg. And whenever I try to prove u substitution, I always get confused. It's kind of the same same sort of confusion. Substitution proofs, if you don't start out on the right foot and you don't have a really clear understanding of what you're trying to show, I've been very vague here. I've just been saying this maps to this, but I haven't told you which one you start with, which one you end with. Mm-hmm. So I've given you a lay of the land. I haven't actually told you how to get into the Jeep and drive from one place to the other, so to speak, But this is a very exciting technique, and a lot of the reason complex variables is taught to electrical engineers. And
isn't that like the same problem, but you could just like flip your frame of reference? Like the.
It's kind of that. That's the question, is what's easier to solve, right?
Yeah.
So, so the corresponding hyperbolic version of this is, the question is like, okay, so you can look at a standard lexicon of functions over the hyperbolic numbers and ask the question, what about conformal mapping there? Is there such a notion? I'm pretty sure we'll be able to prove the transport of solution theorem there, just the same. Like, if I have a solution and, you know, I look at a hyperbolic map from one place to, from the x plus jy plane to the u plus jv plane, there's going to be like a correspondence between solution to the wave equation. And so what I'm interested in is, like, can you find sort of the analog of these kind of like super nice, you know, oh look, we can solve the Laplace equation on an annulus, or we can solve the Laplace equation on a half plane. Can you find the analog of those nice solutions for the hyperbolic case, and then illustrate how you can take that nice solution and feed it to some sort of awful hyperbolic map and get a solution to something that's really unpleasant by just using this idea of conformal mapping in the hyperbolic context? I think it should still work. This is how we solve problems around, like, so like, you have like fluid flow going through corners and stuff. There's transformations which will take like the plane and fold it over into like a quarter plane, and you can get like fluid flow around corners and stuff. It's
I'm not as knowledgeable in fluid dynamics, but
well, I mean, we don't really have any courses on it per se, but
wouldn't the analog of that graph though? I mean, graphically just be another like donut. Just kind of switch to donut.
If I what?
You said like the analog of that. Wouldn't the analog just be another, like the kind of the transformations we did before?
Oh, the thing is, I don't know. I'm not sure. What happens geometrically in the hyperbolic case, because you don't have this anymore. You end up with like the square root of x squared minus y squared or something.
Okay.
The details are not obvious.
Yeah, it's not in fractional linear form, so it's not going to make sense. That way, at least.
Oh, you're talking about.
Never mind that question then. I realize
there was something I was going to do. But for fluid flow, you know, I was talking about how it's electric field and the potential. So in the context of fluid flow, the one is like the flow line, the other one is the stream. Let's see, there's like the flow line, and then there's the
6 o'clock.
what's the name of the other stupid thing? I don't know. One of the components points along the direction in which the fluid is flowing. The other one, what is the other stupid thing called? I think it's called the complex potential or something. I'm not sure. I'm not that comfortable with fluid flow either. It's just not something I spend a lot of time thinking about. Anyway, we will probably pick up more on this next time we meet, which will be a way.